In our previous lecture, we have seen that how we can find out the actual neutral axis and a critical neutral axis. Actual neutral axis can be calculated by using formula bx square by 2 is equal to m times ast into d minus x. And critical neutral axis can be calculated with constant k times d, and k can be calculated as sigma cbc upon sigma cbc plus sigma st upon m. We have also seen for a particular steel, K remains constant. As the steel changes, again for whatever type of concrete mix will be, it remains same. Now we have to have a comparison between the two neutral axes that we have just calculated. That is the critical neutral axis, and we call as xc, and the actual neutral axis we call as x. Here, now I have just shown some figures. This is the cross section of a beam with a width b and depth d. Area of steel is given as m times ast, and distance is x from here. This is the general format for showing the neutral axis and the depth of neutral axis from the reinforcement. When the stress in steel and the stress in steel reaches to its maximum value simultaneously, then such type of neutral axis is known as critical neutral axis, which is denoted by xc. This is sigma cbc, this is sigma st upon m. Stress varies from 0 to sigma cbc and maximum to sigma st upon m. Both are reaching simultaneously to its maximum value, then that neutral axis is denoted by xc. Similarly, when we are calculating the value of actual neutral axis, that is by using the bx square by 2 is equal to m times st into d minus x, we find either that the actual depth of neutral axis is either more than xc or less than xc. Now, when it is more than xc means the Cj of this section is in the steel section, in the steel zone. Means we are providing the more steel, hence the Cg shifted toward the steel zone. When we are providing the less steel, concrete will be rich, and at that stage we will find that the depth of the actual neutral axis is less as compared to that of the xc. Now we have got two things in our mind. Number one, when x is greater than xc, that is I am talking about this case, we are providing the more steel, so we can call this as the over reinforced section. Similarly, when condition number 2 says that when an x is less than xc, this is xc, you can see that xc is more as compared to, so x is less than xc means we are providing less steel, means concrete is richer, hence the neutral axis is shifting in the concrete zone. Under such circumstances, when x is less than xc, where the concrete is more means we are providing the less steel, that is called under reinforced section. So there are two sections, under reinforced section and over reinforced section. I will repeat, when actual neutral axis is greater than critical neutral axis, it is over reinforced section. When actual neutral axis is less than critical neutral axis, which is called under reinforced section. Now, I am drawing another figure, area of steel, x d minus x. Now, the force is 0 over here, the maximum stress is sigma cbc. The average stress is sigma cbc by 2. What is the total concrete area? The total compressive force is nothing but the total area of the concrete and average stress of concrete. Because the stress is 0 over here, maximum at this point, so average is 0 plus sigma cbc by 2 into b into x. That will give you compressive force denoted by Ce. C only. We can call it C only. C. Similarly, stress in steel into area of steel gives the tensile force T. This is called tensile force T. So we have got two forces, compressive force C and tensile force T. But now this is a triangular varying from 0 to sigma CBC. The compressive force acts at a distance of the CJ of the triangle from the top at a distance of x by 3 from here, and this I have written it is x by 3 from here. Now we know that C is equal to T. We know that C is equal to T. When the two equal and opposite forces are simultaneously acting on a body, then that form a couple. And the distance between the forces is called arm of a couple. And the moment of couple is nothing but either this force into this distance or this force into this distance. So we are interested to find out the arm of a couple and then the moment of a couple. We will go for our next part over here. I will repeat that same figure. Compressive force, that is average stress into area, sigma CBC by 2 into B into X, and this is sigma ST into AST. The distance between the two, which we call as the arm of a couple in the case of the couple, but in the case of RCC, that arm of a couple is denoted by lever arm. It is denoted by lever arm. So what is the distance of that lever arm right from here to here? Total depth is D. This CJ acts at a distance of x by 3 from here. So total distance D minus x by 3, that will give the value of lever arm. And the moment of resistance for the concrete will be force in concrete into lever arm. That is sigma CBC by 2 into B into X. That is compressive force acting at D minus x by 3. Just see. In the first case, in the case of compressive force, sigma CBC by 2, that is average stress, multiplied by B into X, that is the area, that will give the total force, multiplied by the arm of a couple, we can call the lever arm. This is nothing but total bending moment, or here in this case we call it the total moment of resistance. This is called total moment of resistance, and it is denoted by MR. It is denoted by MR, which is in short written as MR, means nothing but the moment of resistance, because it is resisting the external force coming over the beam. These are the internal forces which are resisting the external loading moment, and that's why we call it the moment of resistance. This is for the C. Similarly for the T, stress into arm of a couple, that is sigma ST into AST is the stress into area due to tensile force T. D minus x by 3 again is the arm of a couple, we can call the lever arm. So for tensile stress it is sigma ST AST into D minus x by 3. For compressive force, sigma CBC by 2 into B into X into D minus x by 3. Now we have to consider two moment of resistance, one for the compression zone and another for the tension zone. The question is, which formula is to be used when? The problem will be very simple. Here, when we saw this figure over here, again you will find, when x is greater than xc, means it is over reinforced. Means who is failing? Concrete will reach to its maximum value and it fails. Concrete will reach to its maximum value and it fails. So when x is greater than xc, the section is over reinforced. At that stage, we will have to calculate moment of resistance by sigma CBC by 2 into B into X into D minus x by 3. Similarly, again come across over here, when x is less than xc, means neutral axis is shifting towards the concrete zone, means we are providing less steel. We are providing the less steel, hence concrete is richer and it is shifting towards the concrete zone. So moment of the steel will reach to its maximum value and it fails. under such circumstances, we'll have to find out the moment of resistance considering the tensile force and the lever arm. That is sigma st into ast into d minus x by 3. Again, I have written when x is less than xc, it is under reinforced section. It is over x is less than xc. It is under reinforced section. Then still fails, so it is sigma st ast into d minus x by 3. And when x is greater than xc, means it is over reinforced section. Concrete fails earlier, then steel fails earlier. I have committed some mistake. When x is greater than xc, when x is greater than xc, it is over reinforced section. The concrete will fail earlier and not the steel. So here I have committed mistake over here. Instead of this, it should be taken just in the reverse direction. When x is less than xc, it is under reinforced section. So we will have to use this sigma st into ast, this formula. This formula is to be used here. Because under reinforced section, steel fails earlier. So this is the moment of resistance. So when x is greater than 3, it is over reinforced. Steel reaches to its maximum value? No. When x is less than, it is under reinforcement. This is this. When x is greater